Hi everyone, my name is David, and today our group is here to present the paper on convex optimization. So our group members are Tuluhan, Akbulut, Sam Lobel, and myself, Royu Tao, or David. So let's get started. So first, I'm going to start off with introducing convex optimization, and then I'll be describing the conjugate gradient method, which is a popular method used for solving systems of linear equations. So, since this is more of a background paper for this class, we first briefly go through what is convexity. First, there are convex sets. So a set C is convex if the line segment between any 2 points in C lies within C as well. This is denoted by the interpolation between x1 and x2 here with the parameter theta. This is represented by a chord between x1 and x2. So the chord between any 2 points in this set C lies in C. So in this non-convex set, this chord has areas that lie outside of the set C, and this is the set C. So next, convex functions. A convex function is a function which takes as input a convex set and outputs a real number. For a convex function, additionally, the output has a similar property to convex sets, where a chord drawn between two input-output pairs always lies above the function. So this is the function here, and the chord between any 2 points always lies above it. This is represented by the inequality here. So given this short background, we asked the question, why do we care about convex functions for optimization? The key to the algorithmic success in minimizing convex functions is that these functions exhibit a local to global phenomenon. So what I mean by this is that the first order Taylor approximation at any given point, or the first derivative at any given point of a convex function is a global underestimator of the convex function. So the converse is also true. So what I mean by global underestimator, any gradient at any point on this function will always lie below the function itself. So this is an extremely helpful property because this inequality here, which represents what I just said, this inequality shows that the gradient at if the gradient at f of x is 0, then x is a global minimizer of the function f. With this in place, this monograph presents methods of minimizing convex functions. So we will begin by discussing the conjugate gradient method. So conjugate gradient. As with the Richardson iteration method discussed in class, the conjugate gradient method also tries to solve the system of n linear equations, denoted by ax equals to b, where x is an unknown vector of size n, b is a known vector of size n as well, and a is also a known square symmetric positive definite matrix of size n by n, similar to the setup we had in class for the Richardson iteration method. So to solve this system of linear equations, what we can do is define a convex objective function, a convex quadratic objective function here. So taking the first derivative of this function, since a is symmetric, we get the first derivative ax minus b. So by the first order conditions described before, f of x is minimized at the solution when x satisfies ax equals to b, basically setting this equal to 0 and rearranging. Now, let's describe the naive algorithm to try and solve this objective function. This objective function is a quadratic objective function here is shown here in where n is equal to 2. So we first describe the steepest descent algorithm. So to do so, we first describe a few terms. The error term at time step I is how far away you are from the solution at that time step. This is denoted by E of I and is simply the difference between the current solution x of I and the actual solution x. So next, the residual at time step I is essentially how far from the correct value of b is x, how far away from the correct value of b is ax of I. It's also the first derivative of the objective function, so whenever you see r, just think of this is the first derivative at point xi. Finally, the method of steepest descent has the update function here. At time step I plus 1, xi gets updated in the direction of the first derivative, which is r of I, or the residual, with a step size of alpha I. So this brings up the question, what should this step size be? Seeing as we already have a gradient direction and a point that we start with, these two combined describe a line of steepest descent represented by the contours of the objective function in the left figure here. As we can see this, we have x0, which is the point that we're trying to update. And this is, since we have a point and also a gradient direction of steepest descent, which is this, we have a line. And so we're trying to find the point on the line which minimizes this objective function here. We take a step size that will take you to the minimum of the objective function along this line, like I said before, denoted by x1 on the right here. We can find this minimum by simply setting the derivative of the objective function with respect to alpha and setting it to 0. This seems great, but we do have issues with this algorithm. The biggest issue being that there's a lot of overlap between the directions of all the iterations in this algorithm. As you can see here, this is a graphic of the steepest descent algorithm running, and we see there's a lot of overlap between different gradient directions between all the different steps. This causes the rate of convergence to be not great and depends heavily on the condition number kata described in class, or the skew of the objective function. The skew of the objective function and where you initialize, essentially. Instead of using gradient steps with lots of overlap, we can pick n orthogonal search directions and only use these search directions in our updates. This implies that there are no overlapping search directions in all our updates. We also span the entire n-dimensional space, since n mutually orthogonal vectors span R of n. These are represented here by d of 0 all the way until d of n minus 1. In this case, the step sizes alpha I matter a lot. In order to line up correctly for all of our updates. For this algorithm to work, we need a new notion of orthogonality. Two vectors are orthogonal or conjugate if their A norm, as described in class, is 0. So we need to search directions which are all mutually orthogonal. We begin with describing our algorithm. Let's first assume that we have these DIs and describe an algorithm using them and show that we will show that it converges in n steps. We first begin with this update rule, where we update x of I with a scaled search direction d of I. This is very similar to the method of steepest descent, except the search direction is di instead of the first derivative r of I. We begin with an intuition of the proof. For each search direction di, if we pick the right alpha I step size, that means that the update alpha I times di reduces the error in the di direction completely. After all the errors in the n directions are reduced completely, and since these search directions d0 to dn-1 span the entire space of Rn, we have no more directions to possibly update and no more errors to possibly clean. Our error should be 0 then. This begs the question, how do we pick the step sizes alpha I such that the error gets reduced completely? We find the step size by first noticing that the starting error term can be decomposed and written as a linear combination of all our n search directions, since the search directions span R of n. Each search direction d of j is weighted by some delta j. We find these delta j's by leveraging two things, A orthogonality and applying the following trick. We first pre-multiply our error by some search direction within the search directions that we have, d of k times A, times the matrix A, which are both given. This gives us the following sum on the right here. Since all our search directions are A orthogonal, this means only the kth value is non-zero in the sum. Rearranging gives delta k values. Now we do a fancy version of adding 0. And we realize the term inside the brackets is actually our error at time step k. Now that we have a way of calculating delta j's, we notice that delta j's are weights for d of j, which sum up to our overall error, e of 0. So what we can do is simply take the negative of these delta j's as our step size. Now we consider the error term at time step I. It's simply the sum of the initial error plus all the updates we've made in the I-1 search directions. Rewriting out all the terms of our initial error and changing our step sizes back into deltas, we get this. The remaining errors in the remaining search directions. This means that at time step n, we have no more search directions, and we have that the error at time step n is 0. With this, we prove that this algorithm that uses conjugate directions converges in at most n steps. Now the last question remains. How do we pick our search directions d of I? If we pick d of I naively, say like modifying the unit vectors representing the coordinate axes, we have to do quite a bit of work to convert these linearly independent vectors into mutually a-orthogonal vectors. This process is done normally in O of n squared time and is called the conjugate Gram-Schmidt process. So that's O of n squared per time step. But instead, we can be smart about picking our search directions. Through a combination of the properties of the span of residuals and rearranging the Gram-Schmidt conjugation, we get the following algorithm with a runtime of O of m per step over the O of n squared that we had before, where m is the number of non-zeros in A. The finalized conjugate gradient method is described by the update rules here on the right. It gets quite complicated, so if you're interested in digging into the math of why this works in terms of picking conjugate directions, please refer to the manuscript referenced for more details. And that's the conjugate gradient method. Here are our references.
I'm Tuluhan. In my part, I will be talking about gradient descent and projected gradient descent. We will check the oracle complexity, and then we will add smoothness and strong convexity assumptions to improve that oracle complexity. So let me start with gradient descent. Here is the standard formula. I will be following a PDF most of the time because this is how I understand the underlying math. So I need this level of detail to understand. I won't be going over all the proofs, but it will be easy for you to follow if you pause the video, because I will go through them. So for gradient descent, this is the equation. And if you get if you try to get intuition, we are trying to minimize the first order Taylor approximation. So this is the equation, familiar equation. But if we minimize this equation, we will just overshoot somewhere else in our convex set, and we couldn't find the minima. We would go too far away. So that's why we are penalizing it with this term, where eta is the learning rate. And if you do the math, and if you just take the derivative of this thing and minimize it, you will find that the next x should be exactly the gradient step equation. Let me also talk about gradient and subgradient. So these are not the definitions of gradient and subgradient, but here we have on our left we have a smooth function, and on our right we have a non-smooth function. So here the difference is, at this critical point we have subgradients, and when we apply gradient descent to both algorithms, on left we can achieve the local minima, but on right we will be jumping from this point to that point, because these two parts are linear, so the gradient is constant. That's why we have a suboptimality there, so we cannot exactly reach the minima based on the learning rate. Because of the learning rate, we will be jumping over the minima. So if we make the learning rate smaller in time, then we can get closer to the minima, but it's not like there's no adjusting as in gradient-based cases. So as we see here, the oracle complexity, oracle complexity means how many times should we evaluate the function value or gradient value, is independent of dimension. So that's why this algorithm is very useful when we are optimizing in very high dimensional spaces. However, we should not forget that the computational complexity is still linear with the dimension size, because we have to manipulate the gradients, right? So gradient has that vector has the size of the space. So now we will talk about projection operator. So if we do gradient descent normally, when we take a step from xt, we may end up at yt plus 1, but this can be out of our convex set. So we need to go, we cannot do that. So we are operating in our convex set. That's where the function is defined, or that's where we can evaluate. So that's why we need to return back to our convex set, and that's why we are defining a projection operator, which finds the point on the convex set which is closest to y. So we are minimizing the norm here. And here is a lemma. So we will use this thing. So the intuition is that this triangle is always, this angle has always an angle, this angle is always larger than 90 degrees. And then that implies this inequality. So the reason is that because it's convex, right? So because of this curvature, this thing should be greater than 90. And that means this norm is, the square of this norm is bigger than the sum of the square of these two norms. And here's a proof, algebraic proof, but I will not be talking about this. And now we will jump to the PDF. So here's the. So we will first talk about projected subgradient method for Lipschitz function. So when we talk about Lipschitz functions, it means the gradient is smaller than a constant, and that is L here. And G is a subgradient, and it is smaller than an L. And X is a convex set, and it is in an Euclidean ball with R. It's just in 3D you can think of it as a sphere, and our convex set lies in that sphere. So here is the claim. So if the learning rate is this, we will have a bound for our suboptimality, which is smaller than RL over square root of t, and x star is the solution. So here is how we drive this. We use convexity and the non-square distribution, and then the important thing is here our gradient. So because of the projection, because of we are doing a constraint optimization, we need to stay in our convex set. So there's a YST plus 1 here. We need to convert this to XS. We need to convert Y to X. And to do that, we are using the lemma, which is this norm, like the, let's say, the distance of Y to a point in the convex set should be always bigger than the distance of the projected version of Y to that same X star, to that same point. So so that's what you can see. So here this thing is always bigger than this part. So then we achieve a telescoping sum, and we sum it over from 1 to t, and then we achieve the proposed rate. So in the book it says we should take eta as r over L square root of t, but even we don't assume that. If we just take the derivative of this thing with respect to eta and try to find the critical point, that will be equal to this. So, and yeah, and here is the suboptimality, and it shows that the suboptimality scales with 1 over square root of d. That means to reach an epsilon optimum point, we need 1 over epsilon square oracle calls. So in this bound, we have in this oracle calls. So this is a bit disappointing because in previous chapters, center of gravity or ellipsoid method had fewer oracle calls, which is logarithm of 1 over epsilon. And now in the next, we will have beta smoothness and alpha strong convexity to improve our algorithm. So let's define the beta smoothness. So this is the definition. The difference of gradients with respect to 2 points should be smaller than beta times the distance on the convex set. That means if this function is twice differentiable, the Hessian should be larger than 0. So if the set is convex, of course the Hessian, if it's twice differentiable, the Hessian should be larger than 0. But if it's beta smooth, that means that the Hessians should be smaller than beta. And here is an important lemma. So here are the steps if you want to follow them. But the important thing this lemma shows is we achieve this inequality. And if we rearrange the terms, my function fx is smaller than a quadratic function, which is x. The term is x minus 1 non-square. So that means if it's always smaller than this, I can always fit a quadratic on top of my function. That means my function grows slower than a quadratic. And then this shows that if you take a gradient step, here's the bound for that gradient step, and here how we drive it. And then so here we will find the suboptimality for smoothness, and it should be this thing. And since we are operating in a Euclidean ball, I will change this norm with r squared. Okay, after using convexity and Koki-Schwarz, we can prove this. Here I skipped some of the proofs because this is the unconstrained case, and in constrained case we will do a very similar proof, and there I will show you. But here, as you can see, our suboptimality is scaling with 1 over t. So that means to reach an epsilon optimal point, we need 1 over epsilon oracle calls. But this was unconstrained. Now we need to show that the bound for the constraint case, where the constraint is we should always stay in the convex set. So previously we showed that each step will decrease the function value by at least 1 over 2 beta times norm of gradient square. So that was here, right? This is improvement by 1 gradient step. So this is good, but we cannot do that because the projection will shorten the steps. So if we go back to projection, this line is shorter than this line. So that means we will do worse with the constraint case, because the gradient steps will be shortened. So here is another lemma, and we define a new gradient. Here's this for the lemma, and then with the help of after applying projection and some algebraic manipulations, we prove that, and we will use this lemma to actually show the bound. So here's the bound. This is the bound for the functions. We assume they are beta smooth. And yeah, this is the and we are optimizing in the convex set. So we are bounded by the convex set. So here is the proof in detail. We are using the lemma we found previously, and then we are doing a proof by induction, which is not here, and then so here we use the lemma, and to summarize, we achieve this bound. So we achieve this bound. So previously in unconstrained setting we had this bound, but now we have another bound, which means we are doing worse. But still, the suboptimality scales with 1 over square root of t. That means to reach an epsilon optimal point, we need 1 over epsilon oracle calls. And as you can see, from 1 over epsilon squared to 1 over epsilon, we improved our oracle complexity with smoothness assumption. And then lastly, we will add convexity. And here is the definition of alpha strongly convex, which is this. So let's get the intuition for this one as well. Our function fy is always bigger than always bigger than a quadratic function. So our function is lower bound by quadratic, and our gradient will flow if we go away far from x. So since this is bound by quadratic, and quadratic functions grow when we get further away from the minimum, that means our gradient will grow if we go far away from x. This will also says that this function is convex, and you should realize that if our function is twice differentiable, the eigenvalues of Hessian will be bigger than alpha. And yeah. So here, after doing the proofs, we will see that adding convexity, only adding convexity without smoothness, will decrease our oracle complexity from 1 over epsilon squared to 1 over alpha epsilon. And if we add smoothness as well, it will be beta over alpha times log 1 over epsilon. Notice that beta smoothness introduces an upper bound as a quadratic function, which is this. And alpha convexity is the dual assumption where we have a quadratic lower bound. So that means that our function cannot grow faster than a quadratic, but also grows faster than another quadratic. And for this to work, alpha should be greater than alpha. Sorry, beta should be greater than alpha. And here we just find convex, so we don't assume smoothness here. We'll just find strongly convex and Lipschitz functions oracle complexity. So the proof is very similar to projecting subgradient, but we add this term. And after doing this, so here we had previously a telescoping sum, but we cannot do it because the constants in front of them are not the same. So after multiplying with S and after arrangement, we have a term, and now we do the summation and we can find this bound. So as you can see, the bound is the suboptimality scales with 1 over alpha epsilon. And if we apply both convexity and smooth function in the constraint case, we will achieve this bound for suboptimality. And here's the proof for that. Sorry, this is a bit more complicated. And here we see that suboptimality scales with this exponential, and that means to be epsilon optimal, we need this on the order of beta over alpha log 1 over epsilon oracle iterations. And for comparison, we will also show unconstrained case with both assumptions, alpha convex and beta smooth. And in that case, so the proof will be in the next page. And in that case, the k, this is a constant that shows beta over alpha. So that constant will be changed to k plus 1 over 4. And that will mean to achieve epsilon optimal point, we have this main oracle calls, which is slightly less than the constraint case. So like because of projection, we are doing slightly worse, but this is, as I said earlier, expected. And here's the summary. Here's the complexities for like how the suboptimality scales for 3 methods. So one important thing is for the subgradient method, the scaling did not change, and for the other methods we were doing worse in constraint case, but for the subgradient method we didn't. So the reason is this. So this is the first page. I think the reason is that our suboptimality in this case bounded by the learning rate more because of this jumping over, because of this overshoot. So that's why it is more dependent on the eta, the learning rate. That's why the projection is the second concern, and that's why it doesn't change based on that. And here is the proof for the unconstrained case with smoothness and suboptimal. No, sorry, strong convexity, alpha strong convexity, and K is the condition number, which is better over alpha, as I said. Okay. This was all. I would like to show the references. So this was the book we were covering, and I got a lot of help from the YouTube channel of Konstantin Karamanis, and Sam suggested this channel to me actually, and this is all.
Hey everybody, this is Sam. I'm going to be going over mirror descent, try to give you some intuition for it. This was chapter 4 of the monograph that we were reviewing. So mirror descent is a generalization of gradient descent. The main reason that we are so excited about gradient descent in this textbook is that it gives you dimension-independent convergence guarantees. So after taking t steps, the thing on the right is your maximum error, and you don't see any n in there, no dimension. The dimension of the space that you're working in doesn't appear. And that's great if you're working in really large problems, but there's always a possibility that the dimension dependence is hiding in the Lipschitz constant. So this on the right depends on the radius, the r, which is like the size of your problem, L, which is the Lipschitz constant, and T, which is the number of steps you've taken. So you don't need to think of particularly evil examples to see that this is true. For example, if you're trying to, let's say, learn y by following your gradient, and your error is in terms of the L1 norm, which is like the Manhattan distance, your gradient is going to be all plus and minus ones, which means the size of your gradient is going to be the square root of n. So even though it's a pretty well-behaved looking problem, your Lipschitz constant is going to scale with the dimension of the space you're working in. So this isn't great if you're in high dimensions. So why do these bounds for gradient descent depend on L? One way of thinking about it is that L determines how big of a step you can safely take without your function changing too much. So if you want to be safe when you're updating your function, if you know that it can change rapidly, you're going to want to take smaller steps. So this motivates a different way to measure the size of a gradient, which we call the dual norm. So remember we were saying that a big gradient means that a small step will take you farther. So if we look at it in that way, you can get the size of the gradient by saying, how far can I get? What's the farthest I can get if I take a step of size less than or equal to 1? So that's what this equation is showing. You're saying the max value of, if you choose a vector with size less than or equal to 1, and you go in the direction of the gradient, how far can you get? And so what's nice about this is that in general, we measure the size of a gradient in terms of its just like Euclidean magnitude. It's L2 norm. But this, notice that there's no 2 at the bottom of that norm. This actually works on arbitrary norms. And the star on the left-hand side denotes that this way of measuring the norm of the gradients is called the dual norm. So this is the dual norm to whatever norm we're using to measure the size of x. And so for example, if our norm was the L2 norm, we'd be picking an x that is within the unit radius ball. But if it was the L1 norm, for example, we would be picking it from within everything that's bounded by distance 1 of the L1 norm, which is sort of more like a diamond shape. So that's the difference. Yeah, so this lets us define a Lipschitz constant for non-Euclidean norms, which is great because we know that gradient descent depends on the Lipschitz constant, and maybe we can define a Lipschitz constant for different objective functions such that it doesn't have a dependence on the dimension. Okay, so now we have this sort of idea that gradients, it can be measured in size by how far you can go when you take a step. So let's actually sort of think about the gradient update in that framework. So the gradient update usually is written like this, pre-projection, which is you start at a point and then you follow the gradient from some step size and you end up at a new point. But another way we can write this is by saying you start at some point and I want to end up at the point that minimizes following that point and going in the gradient, but doesn't have too big of a distance from where we started. So the derivation on the bottom, you just take a derivative of that and you pretty easily get the same thing. The intuition is that a big gradient, you'll go farther before the normalization kicks in. The regularization kicks in, I'm sorry. So you update to a point that minimizes your linearization without getting too far from where you were. So that's just an equivalent way of thinking about the standard gradient descent update rule. And this is something that might be more clear how we can generalize to non-Euclidean norms. So that's what mirror descent pretty much does. You start with the gradient descent update rule, where you're choosing your next point based on following your gradient but not getting too far from where you are. And mirror descent replaces the concept of too far, goes from the L2 norm to using something else, which we call the Bregman divergence of a function phi, where phi is something we call the mirror map. So this essentially is just a better way or a new way to measure distance. It's not actually a metric, it's a divergence. But it's a new way to measure distance that will give us sort of a better derivation of convergence bounds. So you're still following the gradient, but now your concept of how much you get penalized for going too far is not by the Euclidean norm. Okay, so I kept the update rule at the bottom so we can remember why we care about this stuff. The Bregman divergence is that D thing, and it is sort of our measure for how different the new point is. This is the formula for it. The first two terms are the difference between our mirror map function phi, evaluated at x versus y. And then the third term is the linearized estimate of the difference between those two functions, between those 2 points. So you can think of the mirror map as defining the difference between the linearization of phi and the actual phi. So one way to think about this, considering how we were talking about gradients being defined by, or how we were talking about not wanting to take steps that change your function too much, is a small Bregman divergence means that you should trust your linearization in that area, and a large Bregman divergence means that you shouldn't. Okay, so we've defined what the Bregman divergence given a mirror map means. So what's a mirror map? A mirror map is pretty much just a function from your space to a real number, such that this is taken straight from the monograph. It has to be convex and differentiable. The gradient needs to take on all possible values, and the gradient needs to diverge at the boundary. So phi, these are sort of a little hard to intuit, but phi helps you define your Bregman divergence, and you want your Bregman divergence to measures how your Bregman divergence measures like how much it costs to go some distance away from where you were, and you want that to go to infinity when you're at the boundary, because you don't want to escape the boundary of your space. So that's where the third term comes from. And yeah, it's just a divergence. It measures some sort of like distance-like quantity. So now that we've defined the Bregman divergence, we've defined phi, the mirror map, we're ready to look at mirror descent, the algorithm. Mirror descent on the bottom is how people actually sort of think about, and implement the algorithm. But for the proof, this is projected mirror descent, and it's a little bit more like how you write out projected gradient descent, where first you get a new point by following your gradient, and then you project it back into your space. So those are those two lines. The projection happens by finding the point with the smallest Bregman divergence between where you are and a point that's actually in your the space that you're considering. And the bound we're going to show looks a lot like the gradient descent bound. If you're given a mirror map and a metric that might not be the Euclidean norm, R squared represents sort of the size of the problem, how much the mirror map's value can change from one point to another. You're optimizing a convex function, and it's L Lipschitz with respect to that arbitrary norm. Then we have this convergence guarantee that again is dimension independent. So yeah, it looks a lot like the gradient descent bound, except we have more freedom because we get to choose phi, and we get to choose the norm, and phi determines what R ends up being, and the norm determines what L ends up being. So hopefully, in more types of problems, you can make that dimension independent or nearly dimension independent. Okay, so now mirror descent to proof. In the upper right hand corner is what we're going for, so we remember it. As you can sort of see, what we're going to want to do at some point is we're going to want to sum up all of the xs's over time to show this bound. And so what we do is we start with the difference between some xs, which is just some sort of point on a trajectory, and this just regular x. And we're going to take that to be x star later in the proof, so that it matches better with the thing in the upper right corner. So first we do the standard convexity thing where we bound it by its linearization. Then we use the update rule definition for mirror descent to replace the gradient at xs with these quantities that are from the gradient of the mirror map. Using the definition of Bregman divergence, we can replace those two quantities with three quantities that are just Bregman divergences. So this is nice because now we're just in this sort of Bregman divergence space. And then finally, we can use something. We can use the triangle inequality. Although the Bregman divergence is not a metric, it does satisfy the triangle inequality to turn that last term into two terms. So what's nice about this is that the first and the third term, remember we're going to sum all these things up. The first and the third term, it's something at xs minus something at xs plus 1. So when you add all those things up, they're going to telescope. So you're just going to be left with the first thing, which is going to be x1, and the last thing, which is xt, the first thing minus the last thing. And then the second and fourth term do not telescope, but we'll deal with those in a second. So I brought that up to the top. I rearranged. The first two terms are going to telescope, and then the third and fourth term are not. We can't telescope the last two terms, but we can bound them, which is shown below. I don't really have much intuition, but it's all problem-specific quantities. And now we want to sum everything up to get it in the form in the upper right-hand corner. So when we sum everything up to telescoping terms, we're only left with the first term, which is the Bregman divergence between x and x1, minus the last term, which would be the Bregman divergence between x and xt. But we can upper bound that by just, since Bregman divergence is always positive, by just axing the subtracted term. So we're just left with this one Bregman divergence term and this problem-specific constants. The Bregman divergence term is related to that quantity r, which is sort of like the maximum distance in mirror map space between your starting point and any other point. And we set our step size to this quantity. And when we plug everything in, we are left with the fact that the bound is upper bounded by something with no dimensions in it, just like projected gradient descent. The proof is very similar. It's just dependent on this r and this l, and then there's the same 1 over square root of t dependence in here as well. And so this is really nice. Again, the goal is that we can now pick our mirror map and pick our metric to make these two things small and dimension independent. So as a quick summary, we like gradient descent because it has dimension independent convergence guarantees. But that's only true if L has no dimension dependence, which is not always the case, even in pretty simple objective functions. Mirror descent lets you pick a norm and a mirror map, and you can choose your norm so that L is dimension independent, and you can choose your mirror map so that R is either dimension independent or nearly dimension independent. And then those are sort of two simple choices, and then that gives you a optimization algorithm, and it gives you pretty simple plug-in dimension independent convergence guarantees. And intuitively, if we look at the sort of more standard form of the update rule that we use, this relies on using Bregman divergence as sort of your distance metric for how much to update in any direction, instead of the L2 norm for your problem. Besides the textbook, or monograph, which was really great, special thanks to Konstantin Karamanis' YouTube videos, which really helped me understand this a lot better. And he's got a whole convex optimization textbook to go through if anybody who's watching is interested.